In this particular class, we will discuss about DSP architecture and algorithm concept. The topics are present in Module 3, Architecture for Programmable Digital Signal Processing Devices. So in this data addressing capabilities, we have 4 different types of data addressing modes, and also special addressing modes. We have 2 types of special addressing modes. One is modulo addressing, also called as circular addressing mode, and also bit reversed addressing mode. In the first data addressing capability, we have the first one, data accessing capability of a programmable digital signal processor devices is configured by means of its addressing modes. So we have here the addressing modes. Summary of the addressing modes used in uh, programmable digital signal processors are discussed one by one. The first addressing mode that we have here is immediate addressing mode. In the place of operand, an immediate value is used in the instruction format or the sample format. Example of that is add hash immediate value. Here what is going to happen? The accumulator content will be added with the immediate value and the result is stored in the accumulator register A again. Whereas in case of register, wherein the registers are involved here, the operand content is a register content. Add register, here the accumulator register A is added with the content of the register, general purpose register, and the result is again stored in the accumulator register. And again we have a direct addressing mode. The second one is register. The third one we have is the direct addressing mode. In case of direct addressing mode, the operand is the memory address registers. We have certain memory address registers. So this is represented as MEM, memory address register. Add MEM, then MEM plus A is extended to A itself. Then the fourth one we have here is indirect addressing mode. In indirect addressing mode, memory contents with address in the register will be added for this particular example. If there is any asterisk mark, star address register, the content which is stored in the address register is added with the accumulator register and again it is stored in the accumulator A. So these are the sample format with respect to addition instruction is concerned with respect to programmable digital signal processing uh, uh, devices. And then we have the each and every data addressing, general data addressing modes explanation here. In this addressing mode, data is included in the instruction itself. The immediate value, the value hash 1234H or some value hash 1111H. So this particular value will be included in the instruction itself. Whereas in case of register addressing mode, one of the register will holding the data and register has to be specified in the instruction. So which register we are using, so that has to be specified in the instruction itself. The third one we have here is the direct addressing mode. In this addressing mode, the instruction holds the memory location of the operand. Example, select what we have learned, add 1234H. Add 1234H, wherein the 1234 hexadecimal value is added with the content of the accumulator register and then it is stored in the accumulator register again. So the instruction holds the memory location of the operand. So this may be the memory location where it holds the memory location of the operand in case of indirect addressing mode. In case of indirect addressing mode, the operand is accessed using a pointer. A pointer is generally a register which holds the address of the location where the operand resides. So that is another example. Say if I am going to have some address register, say add star address register. Some address register is there. So for this particular star address register, a pointer is generally a register which holds the address of the location where the operand resides. So few more examples we'll discuss in the next coming slides. So in indirect addressing mode, we have different variations of indirect addressing mode based upon whether we are performing the increment operation, decrement operation, or based upon whether we are performing the addition or subtraction. We have this 8 following different types of indirect addressing capabilities. The first indirect addressing capability that we have here is post increment. Sample format for post increment is add star address register plus. So in this case, what is going to happen here is A is equal to A plus star address register. First operation takes place. Since it is a post increment, addition takes place first. Then the address register is incremented one more time. This is called as post increment. Whereas in case of post decrement, since it is with respect to add instruction, add star address register minus, here if you just observe, addition takes place first, then the decrementing of the value of the ADDREG takes place. So that is ADDREG is equal to ADDREG minus 1. The third one we have here is pre-increment, and the fourth one we have here is pre-decrement. Before performing the addition, we are going to increment the address register and we will decrement the address register value. That is, address register is equal to address register plus 1. This incrementing takes place. Later, the content stored at the new value of the address register are added with the accumulator register. Again, pre-decrement, we have address register is decremented first, then the content of that particular value, a pointer which is pointing to that particular value, that address register is added with the accumulator and it is stored in the accumulator register. Again, we have the fifth one. The fifth one is post add offset. In case of post add offset, add star address register, comma offset register plus. First, addition of this A plus add star address register content will take place. Then add register will be updated with a new value by performing the addition of address register plus offset register value. In case of post subtract offset, what is going to happen here is, since it is post subtraction operation, first the accumulator is added with the old value of star address register content, and then again address register will be equal to address register minus 1. The subtraction takes place after performing the addition operation. It is called as post add sub post subtract offset. Whereas in this case it is post add offset. So the after this fifth and sixth one, we have the next seventh one here is pre-add offset. In case of pre-add offset, since it is addition is prior to performing the instruction execution, I have to subtract the offset value from the address register value. The seventh one we have is the pre-add offset value. The pre-add offset addressing mode. In case of pre-add offset addressing mode, the example format is add offset register plus, comma, star address register. Address register is updated with a new value by performing the addition of the old value of the address register plus the offset register value, and then addition takes place for A plus star address register. That is the content which is stored at the address register address location that will be added. So this is called as the pre-add offset. And then the eighth one we have here is the pre-subtract offset. In case of pre-subtract offset, add offset register minus, then star address register. What is going to happen here is, the first thing, processor will perform the subtraction operation, subtracting the value of the offset register from the address register, and the new updated value is stored in the address register. This new updated value is pointing to some data. That data will be added with the accumulator. So this is called as the pre-subtract offset indirect addressing mode. There are 8 different indirect addressing mode variation. First is post increment, post decrement, pre increment, pre decrement, post add offset, post subtract offset, pre add offset, pre subtract offset are the different things. Coming to a simple problem on the indirect addressing mode. So we have a problem like this. What are all the memory addresses of the operands in each of the following cases of indirect addressing mode? In each case, what will be the content of the address register after the memory access? Assume that the initial content of the address register and offset registers are 000200 hexadecimal and 0010 hexadecimal. This is address register value and this is offset register value. First case, one, second one, third one, and fourth one in this case. Add star address register minus, add plus star address register, then add offset register plus comma address register, star address register, then add star address register comma offset register minus. First, we'll consider the first one, add star address register minus. It's a type of indirect addressing mode wherein we have a symbol minus and after the register we have the symbol minus. Hence, it is called as post decrement indirect addressing mode. It's a post decrement indirect addressing mode. So in this post decrement indirect addressing mode, what will be the operand access? The operand access that we have here is address register. That address register is 0200 hexadecimal. What is the address register content after the access? Since it is a post decrement operation, decrement by 1 takes place after the operand access. Hence, 0200 minus 01, that is nothing but 01 FFH. That is 0200 and then subtraction with 001. Hexadecimal, borrow for this is 16, 16 minus 1 is 15, 15 in hexadecimal is F. When I take a borrow, this fellow becomes maximum value 16 minus 1, that is 15. 15 is nothing but F in hexadecimal. Then this is 1 and then this is 0. This is 01 FF hexadecimal is the address content after the access. Second one we have here is ADD plus star of ADD REG, that is pre-increment indirect addressing mode. It is an pre-increment indirect addressing mode. In this case, 0200 plus 01 hexadecimal addition takes place first because it is pre-increment operation. So since it is a pre-increment operation, first it is happening is 0200 plus 01, that is 0201 hexadecimal. Then address content after the access, the address register content, ADD/REG content after the access is 0201 hexadecimal. Coming to the third one, add offset register plus star address register. If you just observe here, we have offset register plus operand before the address register operand. Hence, it is pre. We have a symbol plus. Hence, it is add offset. So this is pre-add offset indirect addressing mode. Since it is pre-add offset indirect addressing mode, the operand address will be added with the offset value. Address register value plus the offset register value is 0210 hexadecimal. Address content after the access is 0210 hexadecimal. Coming to the fourth one, address register, your addition of address star address register, comma offset register minus. If you just see, the offset register is on after the operand address register. We call it as post. It is a post. Since the negative symbol is there, we call it as subtract. Post, subtract, offset indirect addressing mode. It's a indirect addressing mode. So post add offset indirect addressing mode. 0200 hexadecimal is there here. Then 0200 minus 0010, that is equal to 01F0 hexadecimal. So this is the subtraction. The subtraction here I will teach you. 0200 hexadecimal, 0010 hexadecimal. What is going to happen? 0 minus 0 is 0. Take a borrow from here. It is 16. 16 minus 1 is F. Then 1 minus 0 is 1. Then it is, so 01F0 hexadecimal is the value of the address register content after the access of this particular instruction. So this is one problem in the video exam question papers. So you can expect these questions in the examination. Coming to the next one we have here is identify the addressing modes of the operand in each of the following instruction. They'll be given with some of the instruction. Your job is to just identify whether it is what kind of instruction it is. Since it is hash immediate value 1, 2, 3, 4 is there, it's an immediate addressing mode. So that has been written here. So by observing the instruction, since the symbol is there here, this particular symbol is there, and along with 1, 2, 3, 4 H, it is called as immediate addressing. Then add, like you have an add 1, 2, 3, 4 hexadecimal. So since the address is there here, so 1, 2, 3, 4 hexadecimal, it is called as direct addressing mode. Coming to the case of add star AR plus, it is plus is there, it is increment. After the register, AR register, we have plus symbol, hence it is called as post increment indirect addressing mode. Coming to here, offset is first before your auxiliary register. So hence it is called as pre-subtract, since the negative symbol is there here. So it's a subtract, pre-subtract, offset, indirect addressing mode. So these are the some of the samples where we need to identify the addressing modes for the following instruction. Afterwards, we have special addressing modes. The special addressing modes, what we have here is the implementation of some real-time applications in DSP uses, DSP algorithms uses this kinds of special addressing modes, like for calculation of circular convolution or calculation of fast Fourier transform of a sequence. So in such cases, we need this two special addressing mode. One is called as circular addressing mode and second one is called as bit reversed addressing mode. Circular addressing mode is also called as modulo addressing mode. It is also called as modulo addressing mode. So in case of circular addressing mode, what is important? In case of circular addressing mode, we require a pointer register to hold the current location. We also require a start address register to hold the starting address of the buffer, end address register to hold the ending address of the buffer. So three registers are involved in case of circular addressing mode. One is pointer register to hold the current location, start address register to hold the starting address of the buffer, and end address register to hold the ending of the buffer. So here what happens, the data samples coming continuously in a sequential manner. So here the data are stored in the case of circular buffers are used for the circular addressing mode. The circular buffer, the data samples are stored sequentially from the initial location till the buffer gets filled up. So once the buffer gets filled up, the next data samples will be get stored once again from the initial location. Now what is the meaning? Say I have, this is the circular buffer. The circular buffer is starting with 0 and ending with F. Say it is starting with 200 and it is ending at 200 F hexadecimal. In this particular case, the buffer size is 200F minus 200 plus 1 is the buffer size. Here the buffer size will be F plus 1, that is 10 hexadecimal. So after storing all the data in this particular location, if any data which is coming to another location, immediately this new data will be stored in the circular buffer location itself. So it should not go beyond this, or it should not go below this particular value. It has to be, the values has to be within this buffer size of 10 hexadecimal. This process can do forever as long as the data samples are processed in a rate faster than the incoming data rate. So generally in case of circular addressing mode, we have three registers: pointer register, SAR register and EAR register. We have a special cases of circular addressing mode. The special cases of circular addressing mode here is if the value of start address register is lesser than the end address register. Example, 2000 hexadecimal with 2000 F hexadecimal. In this case, what happens? 2000 is less than 200 F hexadecimal. So in such case, SAR is less than EAR. Then what happens? There may be a chances that my updating pointer is greater than EAR. This is the updated pointer. So if this updated pointer I'm having, say here, means updated pointer is greater than EAR, means this is the first case, case number 1. Second case, same situation, but my updated value, the updated pointer value may be, the updated pointer value may be below the SAR, that is less than SAR. So this is my updated pointer. So what is going to happen? That is second case. Coming to third case, say I may have an SAR and EAR like this. The SAR value, start address register value, is greater than the end address register value. In such cases, we'll be having again the two cases. One is updated pointer is greater than SAR. What is going to happen? And we may also have an updated pointer that will be less than EAR. Say that will be less than EAR. So this is less than EAR, whereas this pointer is greater than SAR. Coming to here, the first one is greater than EAR and here it is less than SAR. Four different cases we have, special cases we have in case of circular addressing mode. How to calculate the circular addressing buffer size? The circular addressing buffer size, or it is also called as length, is calculated as end address register minus start address register plus 1 for the first and second cases, and start address register minus end address register plus 1 for the third and fourth case. In this case, say you may have 2000 hexadecimal for EAR and 2006 hexadecimal for SAR. What happens now? 2006 minus 2000 plus 1. So in such case, 6 plus 1 is 7. 7 is the buffer length. So buffer length is equal to 7, or buffer length is also called as size is equal to 7. But in this case, 2000 F minus 2000 plus 1. So I'll be having here, it is F plus 1, 10 hexadecimal. So 10 hexadecimal is the buffer size or the length used in the first example. That is 1 and 2 examples explained. 3 and 4 example explains, we have this. So we have, based upon these 4 cases, we have an algorithm called as pointer updating algorithm. We'll discuss about the pointer updating algorithm. In this case, the updated pointer is equal to pointer plus or minus increment or decrement. Pointer may change, pointer value may added with some increment value or subtracted with some increment value. So in such cases, we'll be having the new updated pointer value. If there is a new updated pointer value, we'll check that if start address register is less than end address register, and also the pointer is greater than EAR. The case I'll write here, my SAR is less than EAR value, right? This is my SAR, say 2000 hexadecimal. So this is 2000 F hexadecimal. This is my end address register. In this case, if the EAR value, pointer value, that is the updated pointer value, is greater than the EAR value, greater than this, say 2012 hexadecimal. This is my new value, 2012 hexadecimal. If this is my updated value, what is going to happen? If this is my updated value, the new pointer is equal to the updated pointer minus the buffer size. Whatever may be the buffer size. We had a buffer size 10 hexadecimal. Now the new value is 2012 minus 0010 hexadecimal subtracted, then the new value that I'll be having here is 2002 hexadecimal. What is 2002? So if this is 2000 hexadecimal, this is 2001 hexadecimal, 1 hexadecimal, and say this may be the new value, updated value 2002 hexadecimal. Now I'm shifting the data from this area to this area. So just observe here, new pointer is equal to updated pointer minus buffer size. We are performing here subtraction since the updated pointer value is greater than the end address register value. And if updated pointer is less than SAR, say I may have an updated pointer value, that updated pointer value is less than the SAR value. Take an example, I may have one FFFE. 1 FFFE hexadecimal is the new value. That new value, updated pointer value, is less than SAR. Is it less than SAR? Yes, updated pointer value is less than SAR. Then new pointer is equal to updated pointer plus buffer size. What is the updated pointer? The updated pointer that I am having here is 1 FFE hexadecimal will be added with the buffer size. Buffer size is 1 FFE0 plus 0010 hexadecimal. This is the updated pointer value and this is the buffer size value. After addition, this is hexadecimal number, E plus 0 is E only, F plus 1 is 0, 1 carry, F plus 1 is 0, 1 carry, 1 plus 1 is 2. What is going to happen here is, because of this, the new updated pointer that I am getting now here is, I'll write it in different color pen. So here I'll be having the new updated value that will appear here. So this is the new updated value, that is 200E hexadecimal. In the similar way, this part can also be explained. If SAR is greater than EAR and if updated pointer is greater than SAR, then updated pointer, whenever it is greater, we have to perform the subtraction operation. Whether this side you may have SAR, EAR, whenever updated pointer is greater, you have to perform the subtraction operation. Whenever updated pointer is lesser, you have to perform the addition operation with the buffer size. So in this new pointer, updated pointer minus the buffer size. Let us explain this with one simple example. Say I have here 2000 hexadecimal. Say I have here 2006 hexadecimal. So this say 7 hexadecimal we'll consider. So for this, what is going to happen? The circular buffer size is 2007 minus 2000 hexadecimal plus 1, that is 8. 8 is the circular buffer size. 8 means I'll be having 1, 2, 3, 4, 5, this will be 6, this will be 7 and this will be 8. Say this is, I'll assume that I have the data, this is 2001, 2, this is for 2, this is for 2 and this is for 3 and this is 4, this is 5, this is 6, this is 7. So this is the data that I'm having. If you just see here, 0, 1, 2, 3, 4, 5, 6, 7. So this many datas I have here. So I'll erase it. So I don't have this. Okay. So for this particular data, see here, and this is, I assume that this is my updated, that is SAR, and this is my end address register. This is my start address register. In this case, 2007 is greater than 200 hexadecimal. Assume that updated pointer is greater than SAR. So I'm going to assume that my updated pointer is 2008 hexadecimal. Or okay, this is my updated pointer. Then what happens? The updated pointer 2008 hexadecimal subtracted with the 0008 hexadecimal, and I'm going to get the answer 200 hexadecimal. This value will be the updated pointer value. This updated pointer will be this, whereas new pointer will be this. Third case we will consider, say for example, the updated pointer value is less than the end address register. Less than the end address register means, say instead of this, I'll take same example, 1FFE. This is 1FFE. Say here I have 1FFE hexadecimal added with the circular buffer size register 0008 hexadecimal. Then what happens? That is 1FFE with 0008 hexadecimal. If you just observe, after E it is F, after F it is 10, then you'll get 16, then you'll have F plus 1 is 0, then you will have F plus 1 is 0, carry 1, then you will be having 2006. The updated pointer will move to 2006 in this case. So this is the circular buffer addressing mode.